So, one of the reasons I want to start today talking about causation is that it sort of starts to come up. So it starts to come up when we're talking about correlational versus experimental designs. We'll talk about that in terms of causal inference. It'll come up again tonight when we talk about effect size and what that kind of means. Does it mean something about cause effect? So I just want to talk about what it really takes before we're able to say something about causation, that is cause effect or causal inferences. So there's some conditions that we have to meet for this. If you ever need a reference for this, these particular set of conditions, these are from Hypotheses. That'd be a reference that anybody I think would respect. And so the first condition would be that, so here we're going to try to say that X is causing Y, right? Whatever X is, whatever Y is, right? Okay. So if we're going to say that, then X needs to happen before Y. Right? If X is going to cause Y, X needs to happen first. Right? You can't cause something to happen in the past, but you can certainly cause it to happen in the future. Right? Okay, so that's just logical. The other thing is we need to have some theoretical rationale for that causality. In other words, we need to be able to explain why it is that X should or would cause Y. And that's not just something that we make up. That's something that we find in the literature. We would have theoretical support from prior researchers, from prior theorists as to why this causation would occur. Okay, and so this is yet another place that we find where we have to be reading the literature. If we're going to do quality research, you have to read the literature. We'll come across another time later in class where if you don't know the literature, you can't do the research. I mean, it's just true. Don't know literature, can't do good research. Okay? We need a theoretical rationale for the causality. It has to make sense. We have to be able to explain it. We have to be able to give some reasoning behind it. Okay? We need a statistically reliable change in the outcome associated with the supposed cause. Now, this is where, in fact, only place so far, these first two are sort of rational, and this third one is our first sort of statistical issue. So we need to be able to establish that, in fact, when X changes, so does Y. Whether X is group membership or X is some sort of continuous variable, when it changes, Y changes. We can do that with any number of statistics, but we need to be able to show that it changes. The other thing is that we need to be able to isolate the effects of X on Y. That is to say, there's lots of possible influences on any outcome that you can possibly think of. There's lots of things that might influence it, right? And we need to be able to establish that this supposed cause, even once we account for other possible causes or other possible influences, is still acting on that outcome. Right? And so one of the examples that I like to use is about murder. Right? So let's talk about people who get murdered for a second. Okay? So it is true that there is a statistically reliable increase, in fact, in the murder rate that is associated with ice cream consumption. There is a statistically reliable change in drownings that is also associated with ice cream consumption. I just got this question the last time I used this example, which was yesterday, of whether those are two separate things or is it like murder by drowning. And so I'm actually talking about accidental drownings and intentional murder. Okay? So both of those things are reliably associated with increase in ice cream consumption. So then, is that sufficient evidence for us to say that eating ice cream causes you to both drown accidentally and murder other people?
I would have killed a lot of people by now if that was the case.
Right. Yeah, similarly.
Or myself.
Yeah. Okay. So you're thinking no? Thinking no. Okay. So then what explains the relationship? There's a relationship there. What explains it?
The weather.
The weather. Yeah. So when do people eat ice cream? When do people drown? Right. Because people do other things in the summer, like swim, right? If you're swimming, you're much more likely to drown than if you're not, right? Because you have your face in water all of a sudden, right? Okay. And like the murder thing, right? So like that one's weirder. That's harder to explain than the swimming thing. Right? If you're like murdering people in pools, I don't know. But actually, when people are hot, they are more aggressive. So there is a general rise in violent crimes in the summer. It just so happens that people eat ice cream in summer because they're hot. So it's not that there's this direct link between ice cream and either of these things. The direct link is actually between being hot and eating ice cream, being hot and being aggressive, being hot and swimming, right? So those are the direct links, but if we just look at these two variables by themselves, we might come to this false conclusion. Probably not because it feels ridiculous, right? This is a great example because it feels ridiculous, so we automatically start searching for other explanations. But there's a lot of other cases where we think, I don't know, that makes sense to me. And we would never search for other variables to explain the potential causation. But there really is this third variable that we need to examine. So that's an example of a third variable problem. There's a third variable that's explaining the increase in both of the things that we've measured. We didn't measure the third thing, but it's the true cause of both of the variables that we've measured. Right? They're covarying because they're being caused by a third thing we never measured. Right? But it's also possible that, for example, there's a mediating variable going on, there's something that's acting in between the two that we've measured, or that our variable doesn't act alone. We need to measure some other causes with it. Right? We haven't really isolated our variable as a cause. So in other words, this is a multivariate world, right? There's very few things that have a singular cause, and without identifying other causes, we really aren't able to make strong arguments for causation. Unless you've really identified those and isolated the effects, we're not able to make strong arguments for causation. Now that isolation is part of why people like experimental design, because you can sort of control for some of that, but the experimental design in and of itself is not enough. It does help with the fourth criterion, but we need more than just that. I say it helps, it doesn't fully satisfy. Okay, so I want to put that information sort of out there as we think about these kind of issues. Okay, so we're going to be talking tonight about hypothesis testing. And we're going to learn our first hypothesis test, which is the z-test. And so all of this builds on the probability work that we did a couple weeks ago, the work with the sampling distribution that we did last week. It's all building up to the point that now we're ready to test a hypothesis. Right? So we should probably start by talking about hypotheses and what they are and how we write them and the nature of those hypotheses. So we really have two types of hypotheses that we'll talk about. There's the null hypothesis and then there's the research or alternative hypothesis. And the basic idea of the null hypothesis is that there's absolutely no difference. Nothing going on, right? Zero. So we'll take the simple case of we're comparing two groups. If we're comparing two groups, the null hypothesis would be that the difference between those two groups is zero. Those two groups are identical. That would be the null hypothesis. The alternative to that, of course, is that they are not identical. Right? They're either identical or they're not. There's no difference or there is. Those sort of be the two options, right? We could also talk about, so for example, when you do like correlational research or sort of regression types of research, we could say there is a relationship, there's not a relationship. So the null would be there's no relationship. The alternative would be there is a relationship. So the null is like there's nothing going on, nothing to see. The research hypothesis is there is. And then, so we could make errors in testing the hypotheses, right? So type 1 error is rejecting the null hypothesis when we shouldn't. The type 2 error is failing to reject the null hypothesis when we should have rejected the null hypothesis. The null is wrong, but we fail to reject it. I'll point out that the language here, we either reject the null hypothesis or we fail to reject the null hypothesis. We don't accept the research hypothesis. We don't accept the null hypothesis. We reject the null or fail to reject the null. Your book talks about, and we'll talk about briefly, the type 3 error. Just the basic idea of the type 3 error is right answer, wrong question. So we can specify directional hypotheses. So we could specify, for example, in a 2-group question, we could say group 1 is going to be higher than group 2. Well, if it turns out that group 2 is higher than group 1, we're going to wind up failing to reject the null hypothesis. In other words, we're going to wind up saying, nope, nothing to see here, right? But in fact, there is a difference. It's just the opposite direction we specified. So because we specified the wrong directionality, it looks like there's nothing going on. But if we'd specified the directionality correctly, we would have found a difference. So it's an example of a type 3 error. When we talk about testing the null hypothesis, NHST null hypothesis significance test, we're not really directly testing the null. We're certainly not directly testing the alternative hypothesis. What we're actually doing is we're saying, let's assume for a second that the null were true, right? We're going to live in a land where we pretend that the null hypothesis is true. If it were the case that in fact there were 0 difference, how likely is it that we would observe the kind of data that we observed? We went out and collected data, right? Otherwise we wouldn't be able to do a test. We have to have data, right? So if it was true that the real difference was 0, how likely is it we would have got the data that we got? Based on that probability, we're going to say either, okay, seems likely enough, or it's extremely unlikely, so I'm going to reject the null hypothesis as a poor explanation, right? So if I'm assuming that there's 0 difference and testing the probability of getting these data, well, if those data are extremely improbable, assuming that there's 0 difference, I'm going to say, okay, so doesn't really seem like 0 difference is a good explanation. I'll reject the null. If the probability is relatively high, say, okay, 0 difference is a good enough fit for this data. I'll fail to reject the null hypothesis. No evidence to reject the null hypothesis. And so this is the basic idea of the null hypothesis significance test. We're assuming that there's 0 difference and testing the probability of the observed data given that assumption. In other words, we're really unlikely to ever actually find 0 difference. This doesn't really happen very much. But is this degree of difference improbable if the true difference was 0? All right. So the significance test that we're going to learn today is the Z-test. But first I just want to make a note about this word significance and the way that we use it. So you probably have heard by this point, people talk about like, oh, that was a significant result, or we found significance, or that kind of language, right? When people are saying that, they're talking about observed differences relative to a probability criterion. And usually what they mean is that probability criterion was less than 0.05, right? That their calculated probability is less than 0.5. And so the point that I want to make is that when someone uses the word significant in relationship to research results, or significance, that carries a really specific meaning in terms of probability, in terms of the statistical result. Because of that, people use the word significant in everyday speech to mean a lot of things, right? But when we're talking about research, we mean something really specific. We're saying we met a criterion threshold for probability. Right? So if that's not what you mean, then don't say significant. There's lots of words that we can replace it with. You could say interesting, meaningful, important is another example. So if I say that's a significant, if I say that the results were significant, there's a significant difference, then that should be followed up with a probability statistic right after it. Right? If I can't do that, that means that that's not the right place to use the word significant. I'll replace it with something like meaningful, important, earth-shattering, I don't know, something, right? However crazy you want to go with it. But not significant because that carries statistical meaning. Okay, great. So the first significance test that we're going to learn is the z-test. It's unusual in practice, but it's really useful because we get z-scores, right? We went to the z-test. So it's just a gentle way to move into the hypothesis testing. But it is unusual in practice because you may notice as we're calculating different tests that you wouldn't want to use this. Not a whole lot, probably, and you won't see it in the literature very frequently. You certainly could use it. It's a valid test to use, but it's just not used a whole lot. The reason why is you have to know a whole lot about the population in order to use it, and we rarely do. So here on this slide, I give the general form for the null and research hypothesis. So the null hypothesis is represented as HO, H sub 0. And so here, against the general form for sort of overall, we would say maybe like the one mean is equal to another mean, right? The alternative hypothesis is typically like H sub 1. If you have more than one research hypothesis, you go like sub 2, sub 3, sub 4, right? And here I've said that the one mean is not equal to the other mean. It's sort of the alternative. Okay. When we talk about the z-test, what we're going to be doing is testing the difference between a sample and a population. Okay. And right. And so because we're testing the difference between a sample and a population, what we wind up doing is saying that we're specifying that the mean of a sample is equal to the mean of its population. Okay. So the alternative to that would of course be that the mean of the sample is not equal to the mean of the population. Okay. I alluded earlier to the idea that we could have a directional hypothesis. So this kind of hypothesis here will be what we call two-tailed. It's non-directional. The reason for the term two-tailed will be really apparent when we look at the sampling distribution here in a second, because we're looking at either side of the sampling distribution has two tails. Right? We'll illustrate that graphically here in just a moment. We could have a directional hypothesis, though. Directional hypotheses are called one-tailed. And in that case, for example, we might have, and I'm going to start with the alternative hypothesis because it'll be a little more intuitive, I think. We could say that the mean of the sample is going to be greater than the mean of the population. Right? Maybe that's our hypothesis because we have strong literature support for that. We would want to only make the directional hypothesis if we really feel pretty strongly about it because of some evidence we have in the literature, probably. Right? We might say the mean of the sample is going to be higher than the mean of the population. That has some empirical advantages to it. But if we do that, then the form of the null changes a little bit to less than or equal to. Because we have to catch all the scores somewhere. Now, you have probably already figured out that this could go the other way, right? So we could specify either directionality. So we could have a non-directional hypothesis. We could have a directional hypothesis, either way. Yeah, it depends on the question and what kind of, and you'd write the question based on your literature support, right?
So if like communication satisfaction positively predicts servant leadership in nurses.
Yeah, and in this case, what we're doing is we're comparing a sample to the population. So, will this group of students have higher satisfaction with their coursework than the general university population? Or like, will USM students, have lower income than students in the United States as a whole, or something like that, right? So, when we think about the level of significance, right, we're going to set a specific probability criterion, and that probability criterion is our level of type 1 error. We control for type 1 error because that's what we're most worried about. The reason we're the most worried about type 1 error, right? So type 1 error is rejecting the null hypothesis when we shouldn't, right? In other words, saying there's a difference when there's no difference. Well, that's a bigger problem, right? Because you're claiming something that's, you're claiming that you have some finding about differences between groups or a relationship that exists or something that causes something else. And it's not true. Right? Well, that's the type of error that we're really a lot more worried about. So that's the one that we directly control instead of type 1 error rate. Sometimes that type 1 error rate is called alpha. Just be careful not to confuse that with the reliability coefficient alpha, because they're both just called alpha. So, easy to do. Usually in the social and behavioral sciences, we set that at 0.05. So anything less than 0.05, we're going to call statistically significant. In the physical sciences, medical sciences, pharmaceutical work, you'll often see it set at 0.01. It's a more conservative value, but then they also have less variance in their findings. So, but typically, in social behavioral work, we're going to use 0.05. So, just this note about multiple tests: if you find yourself in a situation where you think, "Oh, I really need to use like 4 tests to get the job done here," if it's on the same family of data as related measures or subscales of the same, they're somehow related to each other, the tests that you're going to be doing, then what you're doing is you're increasing what we call family-wise error. In other words, the type 1 error sort of like compounds between those tests. So I have this example here, like where 2 comparisons, your true type 1 error winds up being like 0.098 with 3, it's like 0.143. So it starts to add up on you as you do multiple tests. Right, so you're no longer at 0.05 because you've done it multiple times. Okay. So what we do to control for that, the simplest control for that is just divide your type 1 error rate by the number of tests that you'd like to do. Right, so you'd like to do 5 tests, right, divide 0.05 by 5, set it at 0.01, and you've controlled for that issue pretty effectively. The other caveat to that is that if you find yourself with a need to do more than 1 test, the chances are there's a better test. Like next week, we'll learn the t-test. If you're in a situation you think, man, I really need to do like 6 t-tests. Don't do 6 t-tests. There's not a good situation that calls for 6 t-tests, right? Instead, you should probably be doing a MANOVA, and I'm sorry if you don't know that, you need to find someone who does. Right?
Hey, I have a question. So the alpha is the 0.05?
Yeah, we usually set alpha at 0.05.
Okay. But 0.05, like in your first example, under the error rate gets compounded, 0.05 divided by 2, that's not 0.098.
No. So we would divide it by 2 to control for that kind of compounding. It goes to 0.098 because it's adding up. It doesn't add up quite as quickly as so it doesn't add up at quite 2 times, but if we divide by 2, we'll control for it and make sure that it doesn't add up on it. So So what's happening is it's compounding every test you do. There's more error piling on, more error piling on, more error piling on. There's a formula that you can use to show how much error there really is. I don't feel that it would be helpful to talk about that formula, but the quickest and easiest control for it is just divide type 1 error by the number of tests you'd like to do, and you'll wind up just slightly under 0.05 for your total error rate. Again, ideally we wouldn't do multiple tests, but sometimes it happens. Okay, so I mentioned that a non-directional hypothesis is going to be a two-tailed test, right? Well, so first of all, the reason that that's a two-tailed test is that we could have a positive difference, right? On a sampling distribution, a positive difference is going to move us, oops, pen. Oh, there we go. A positive difference is going to move us this way. Okay? Whereas a negative difference is going to move us this way in the sampling distribution. Okay? We're going to use the sampling distribution to figure out the probability of that difference. Okay. Well, so because we don't care in a two-tailed question, we don't care whether it's a positive or a negative difference, right? Well, what we want is to have a difference that is large enough to be less than 0.05 probability, right? Well, so we need to find the region out in the tails, that's out extreme enough, either direction, to be 0.05 probability. Well, so that means I need some over here and some over here that'll add up to 5%, right? It's 0.05. Well, so if I need half on this side and half on this side to add up to 0.05, it's going to be 0.025 on each side, right? Because it's symmetrical. It's a sampling distribution. It's symmetrical. Right? So what we do is we put 0.025 over here. We put 0.025 over here. That adds up to 0.05, right? It's totally symmetrical. And this is a z distribution, so it never changes its shape. So what that means is we actually have a criterion of 1.96 and negative 1.96. Anytime that the z exceeds those values, the probability is less than 0.05. Okay. So now the deal is, if we're talking about a one-tailed probability, right? So let's say I'm looking for a negative difference, right? That means I want a z that's somewhere over here. Well, I don't need to divide that up on each side, right? I want only on one side. Right? So I'm just going to be looking for 5% of the tail over here, which means more shaded area on one side. The end result of that is that we wind up moving in a little bit. So the criteria is minus 1.64, or for a positive difference, going this way, is this positive 1.645. In other words, this is the reason why directional hypotheses are nice if you have the evidence to do it, is you set a lower criterion that you have to beat, right? Because we have to beat that criterion number, be in excess of it, if we're going to say the probability is less than 0.05 and reject the null. So this is why one-tailed tests are good, because you get a lower criterion threshold to beat.
So what does, for example, in the one tail, the 1.645, what does that represent?
It's a z-score,
Okay.
and so we're going to be calculating the z-test values, and we have to have a test value that's more than that. And it's going to be less than 0.05. In fact, so when we look up our test values in the tables in the book to get the exact probabilities, what we'll notice is that we get the one-tailed values in the book. So it's like if you're doing a two-tailed test, you wind up having to multiply by 2 in order to get the two-tailed probabilities, right? And so it becomes really apparent to you as you do that over and over again that there's a real advantage in terms of the probability values you get in having one-tailed tests if you can specify them. So we'll walk through a couple of examples just quickly using the slides, but then we'll do some by hand here as well. Okay, so to do the z-test value, it's slightly different than like, standard scores or z-scores. So it's slightly different. It's going to be the mean of the sample minus the mean of the population over standard error. So the standard error then is the standard deviation of the population over square root of sample size. Okay. So here I have some sample data of 24 participants on college GPA. And the mean of the sample is 3.15, mean of the population is 3.10, standard deviation of the population is 0.63. So then all that we do is take and put these values into the formula, right? So mean of the sample, 3.15, mean of the population, 3.10, standard deviation of the population, 0.63, and then sample size of 0.24. Now already we can start to see why this test is difficult to use a lot of times in practice because we need the mean and standard deviation of the population. Right. Okay, so we subtract in the numerator, we get a difference of 0.05. Simplify the denominator, we get 0.13. Divide through, the z-test value is 0.38. Okay, so we'll look this up in our table in the book. So that starts on 629. And the value is 0.38. Okay. Okay. So let's see. We find the row for 0.38 here. Right. We want the area beyond z and tail, right? Because we're interested in tails now. And we find 0.352. So 0.352 would be the one-tailed probability. Right. Well, so how do we get from one tail to two tails?
Multiply by 2.
That's right. To get from 1 to 2, you multiply by 2. Right. So 0.352 by 2 will give us the two-tailed probability. So P is equal to 0.704 in a two-tailed test. Now, hopefully, we're all in agreement that 0.704 is a lot more than 0.05. Right. So we're not less than 0.05. We would fail to reject the null. There is no significant difference between this sample and the population in terms of college GPA. Yeah, because the probability that we've calculated is 0.704. That's greater than 0.05, right? Which means that there's no significant difference between this sample and the population. No significant difference.
But using the 1.645 for the one tail or 1.96 for the two tail.
Yes, you already know it's not
You already
significant. But if you want that exact probability, you can go to the table. Yep, absolutely.
Writing a paper, you can stop right there.
Well, yeah, so you could already say that P was greater than 0.05, right? But we often want to go ahead and report the exact probabilities if we have the chance. Yeah.
I have a question about what y'all are talking about. So you're saying if the one-tailed score you get is greater than...
Right, so let's say we're doing the two-tailed test, right? So if our score was greater than 1.96 or less than negative 1.96,
Then you already know.
we would already know it's less than 0.05. But we probably still want to go to the table and determine what the exact probability was.
And that's when you have the two-tail is the exact.
Well, we can get the exact for one or two-tail. But it's nice to be able to report the exact probability in a write-up. Yeah, but anytime it exceeds 1.96 or goes below negative 1.96, it's less than 0.05 in a two-tailed test. And then for the one-tailed tests, depending on if it's positively or negatively worded, right, it would either be greater than 1.645 or less than negative 1.645. That would be the criterion for 0.05. But again, we can also just calculate the exact probability from the table.
Which in this case would be 0.3.
Yeah, for one-tailed, or that 0.704 two-tailed. In probability, so I know in the table it goes out to the fourth decimal place. But we typically round to the thousandth place or third decimal place on probabilities when we report them. Okay. Here's another example that we can talk about, sort of the same format. And this is students' value for their coursework. Let's look at, you can see the mean here for the sample, 6.03. The mean for the population, 4.79. Standard deviation for the population, 0.59. So again, we'll just put these numbers straight into the formula, right? So 6.03 is the mean for the sample, 4.79 mean for the population, 0.59 standard deviation of the population, and the square root of 24 is 4.9. Okay, so that difference is 1.24. We divide the denominator through, we get 0.12 for the standard error. Divide that through, we get a z-score of 10.33. Okay, so 10.33 definitely goes beyond that 1.96 criterion, right? So no, it's going to be statistically significant. Let's look at our table, and we have a little bit of a problem. All right, your table stops at 4. We can't even find a probability for it. It's too extreme. All right, so what do you do? Right, here's what we do. What's the one-tail probability for 4.0? Round it to the thousandth place. What's the probability? If we round that to 3, it would be. If we round, look at 4.0, like that's the most you have, right, as far as it goes. If you round that one-tail probability to 3 decimal places, it would be 0. Okay. Now, if we were to have this go out to 10, it would just get smaller and smaller and smaller and smaller, right? So it would be smaller than the 0 that we have now. If we were to multiply that 0 by 2, we would have 0 times 2 is
0.
There we go. Great. All right. Now, you may recall me saying when we talked about probabilities that like there's not a 0 probabilities. Isn't that thing? It would just get like lots and lots of zeros and then some number at the end. Right? But we're going to do the thousandth place. So we're not going to really do that. We could find a table online or a calculator online that would give us that exact probability. You know, it would be something like, 0.03 times 10 to the negative 12th or something like that. You know, we're not going to report it that way because we're just not, right? And if you were to run a statistic in SPSS that had this kind of probability, it would report it to you as 0.000. And you remember we were talking about the fact that we're not going to report it that way because we know better. What we're going to do is we're going to say less than 0.001. And that is going to be good enough for just about everybody in the world. There are some technical methods journals that will want the other kind of reporting, like 0.03 times 10 to the negative 15th or something. But almost everybody will be satisfied with less than 0.001 because like it's certainly less than the criterion. Way less than the criterion of 0.05. And because it's less than the criterion of 0.05, we can reject that null hypothesis. There is a significant difference between this sample and that population in terms of value for coursework. I actually think this is a good example because this happens more often than you would think. When you get negative test values on the z-score, the only time that really matters is if you've specified a direction, like you have a directional hypothesis, a one-tailed hypothesis. Then it matters because it has to be the right direction, right? If it's the wrong direction, you're kind of in trouble. Other than that, it really doesn't matter. We're going to look at the proportion and tail, that column C in the book. We're always going to be looking at that for the probability. The only thing that sign is telling you is what direction the difference is, right? So negative means the population was higher, positive means the sample was higher. Okay? Just telling you which group was higher. If you forget which one is which, well, you can look at the means and determine which one was higher, right? This is another nice thing about a simple analysis like this is that if you know, so for example, here we know that there's a significant difference, right, between the sample and the population. Well, who has greater value for their coursework? Is it the sample has more value for their coursework than the population or less? More, right? So we know that it's different. We also know how it's different because, we're not dumb. We'll look at the, we know it's different and look, here number 6 is more than 4, right? So we can do that. No complicated procedure involved in figuring out which one was higher. Just look. Okay. So what we'll do now is practice a little bit. With some sample problems. And so these are like make-believe problems, right? So completely fabricated. I always like to make that note because I've had the experience in the past of people thinking that fabricated data for class were like real. Like you could tell people about the things you found out in class. Okay, so our first example here, we have scores on a placement exam in math that are supposed to have a normal distribution with a mean of 70 and standard deviation of 18, right? So that'd be our quote-unquote population. It's assumed. It's an assumed distribution, right? But we're saying we're going to say it's the population. Okay. We're going to give that exam then to a random sample of 50 high school seniors who've been admitted to college. So they get a mean score of 67. So assuming that's a true random sample, is their score lower than 70? Okay, so then we have to state the null and research hypotheses. Okay, well, so the research hypothesis is sometimes easier to start with, I think. And so here we're asking, is this sample lower than that population? Right, so we're asking, is their score lower than that assumed population score of 70? And then that means that kind of do the opposite of it for the inverse of it for your null hypothesis. We can calculate our z statistic just using the information that we're given, which is a sample mean of 67, population mean of 70, population standard deviation of 18, and a sample size of 50. So that gives us a difference of -3, and that square root comes out to be 7.07. Okay. If we divide through the denominator, standard error then is 2.55. Okay, that's a 5. Divide that through. Gives us a z-test value of 1.18. So if we assume that everything is is all normal and all that, right? We can look at our table for 1.18. All right, so for 1.18, it's in the third column on the second page. Our one-tailed probability is 0.119. Well, this is a one-tailed test, so we're done at p equals 0.119. So based on that, would we reject or fail to reject the null hypothesis?
Trying to do it straight in my head. Which way is it?
Fail to reject, right? Yeah, in order to reject, it has to be less than 0.05. Right. Great. Okay, so then, why don't you all take a couple minutes and do number 2, where we have an entrance exam for incoming freshmen. In general, it's 550 with standard deviation of 120. This year's freshman class, we've got 90 students with an average score of 582.6, and we want to know if that's weird. So is it lower? This sounds directional, right? Versus in the second question, is it unusual? Is non-directional. All right. So then we'll calculate the z statistic with the information that we're given. We have sample mean of 582.6, population mean of 550. Population standard deviation of 120, and a sample size of 50. Okay. That gives us a difference of 32.6, and then square root of 50.
Sample size 90.
Oh, 90. 9.49. So the square root of 90 is 9.49, which makes a lot more sense. Yeah. Okay. All right. So 32.6, and over divide that through. That'll be 12.64 for a z-test value of 2.58. We look up 2.58 in the table. Is 2.58, gives us 0.005 if we round to the third place, right? But that's a one-tailed probability. Right. Multiply by 2 to get our two-tailed probability, meaning that p is equal to 0.010. And if p is 0.010, right, what do we do? So two options, right? Reject or fail?
Or reject.
Or reject. So there is a significant difference between this year's freshman class and the overall population of incoming freshmen that have come to this university. They are unusual. And in fact, unusually high, right? Significantly higher than the norm. And so, I mean, obviously we'll wind up writing it correctly, right? But don't focus quite as much about getting the style right, and which things are italicized and all that, because we'll come back to that again and again and again. For this exact moment, let's think about how it is that we're interpreting the results and thinking about what it is that we just did, right? Because that's sort of the important part. Is calculating is fun, right? But what's more fun than calculating is being able to do something with that number, right? Okay, so we'll use this second one. And so typically when we start out our results section, the thing that we're going to do is start with a statement of what it is that we did and why it is that we did that, right? And what you have to remember is if you're really writing a paper, before this came lit review and then came methods, right? So you don't have to say a test was given to 50, incoming freshmen that was usually you don't have to do all of that because that's been said in a method section, okay? So what we're coming in is saying we did this test because of this this need to, right? So for example, in this case, what we're trying to find out is if this group is an unusual group, right? So so in order to determine if there was a difference between this year's incoming freshman class and the overall population of freshmen exam scores, a Z test was used. Of course, you could say we used a Z test. That's preferred in APA style, but depending on your field, they may not go for that. Okay. Actually, I'm going to change it. Okay. We used a Z test. But again, depending on the field, which version of that is going to be preferred. Okay, and so then after you say what you did and why, you're going to need to say what you found out. And so in this case, there was a significant difference between this year's freshman class and the overall population of freshmen scores, right? And so then we would go ahead and report the Z-score, 2.58, and the probability of this year's class scored higher on average. Mean was 582.6. And usually when you report a mean, it needs to come with a standard deviation, but this is just example, so there's not enough there to do it, right? Than the population score. Mean is 550 and deviation is 120. Okay. Appears that this year's incoming class scored usually high on the entrance exam in comparison with when compared with other freshmen at the university. So then after we report the results, we always want to wrap up with an interpretive statement, which is actually something people do wrong in results, is especially new writers, is thinking that you don't have any interpretation in results, but you certainly want to give some.
It's just not with scholarly evidence, right?
Right. Yeah. It's answering the research question, but not contextualizing it in the literature. Mm-hmm. So this would be a very simple kind of interpretation. And so hopefully thinking about a little bit of what we would potentially interpret out of this kind of very simple test might help a little bit. I don't know if it does or not, but okay. So what we'll do is we'll take a break, and the piece that we're gonna add on to this is actually not hard at all. So good, right? Okay.
So far, so good.
But
Well,
okay.
there's a load right now,
So the deal is that the hypothesis test, the null hypothesis significance test, has some problems. Okay, and one of those problems is that test is sort of a low bar. Okay, because all that we're really finding out is that the difference exceeds 0. Right. Well, difference exceeding 0 is often not interesting, right? There's very few things in this world that have 0 relationship or groups that have 0 difference, right? Very few things that are literally exactly the same, right? Which means if we get a large enough sample, we'll be able to detect the difference, right? Speaking of having a large enough sample, when you look at the formula for the z-test, for example, we have standard error there in the denominator, right? Well, so what that means is that the smaller that the standard error is, right, the smaller a difference you need in the numerator for that z to be really big, right? In other words, the smaller the standard error is, the easier it is to detect a difference. Which means if I want to detect a difference, in other words, have a significant result, even though I have a really small amount of difference, all I really need to do is get a really big sample. Right? So like if you look at a result where you have, for example, a z of 0.5, right? Well, if that sample size is 50, try changing that sample size to 500, and now all of a sudden, you most likely have a significant z, even with the same exact size of difference. Right? Because nothing else changed, right? Same size difference. The population standard deviation never changes. It's a population. They don't move. Right? So, in other words, we can play a little bit of a game and get a significant result if we just keep getting a bigger and bigger sample. In fact, there's a specific type of analysis that people do to figure out how big of a sample that they would need to get a significant result. I was actually hired by some pharmaceutical companies for a while to do that particular analysis. Because what they say is, we'd like to know.
cheating.
What they say is we want to get the smallest sample possible, to get the significant result, because we don't want to overinvest the resources. Now, whether you believe that explanation or not is your choice. But yeah, you can play games with a hypothesis test. And it's a low bar because all we know is that the difference is not 0. Not 0, okay, that's great. But is it really very much? We don't know. We know it's not 0. Which on that note, a z of 100 and a z of 2, same thing, okay? The only thing we know from either of those is that it's a significant difference, right? There's no such thing as more or less significant. There's significant and there's not significant, okay? There's no gradations of significance. Okay. All right. Which is the other issue with the null hypothesis significance test, is that all you get is a yes or no answer. Is the difference 0 or is the difference not 0? Right? Well, the thing is that we often want to know a little bit more than that, right? So we have, to help us with this problem, effect size statistics. And so let me just say that the effect size statistic and the null hypothesis significance test are 2 separate tests, but they are complementary, and we usually do them together. Okay. In fact, journals will typically, I say typically because it depends on the quality of the journal, not accept a paper that has a null hypothesis test without an effect size statistic for a lot of the reasons we've just been talking about. Right? So the effect size statistic has very little movement based on sample size. There's no yes/no answer. Right? Instead, it's giving us magnitude. How big is the difference? The one we'll look at today gives us the small, medium, large answer. Ones we'll look at later will give us a percent variance explained answer, which, oh, that's great, right? How much variance are we actually accounting for with this? And they give us a really nice supplement to significance testing, because the significance test can tell us, is there a difference? And then the effect size comes in behind that as a complementary test and tells us, okay, is that significant difference meaningful? Is it very large? Okay, so the one that we're going to look at today is Cohen's D. And so you notice, like, I have in the first line of the slide a lowercase italicized d. That's because d is lowercase and italicized. This particular PowerPoint template doesn't let me lowercase stuff in the top bar, so there you go. It should be lowercase, always. All right, so typically the recommendation that people will make as a general, really vague, kind of poor guideline is 0.2 is small, 0.5 is medium, and 0.8 is large. Okay. Now, these are not cutoff scores. These are not criterion scores. These aren't like, oh, I got there, hooray, it's large, right? No, it's not like that. It's not like the 0.05, like you have to get under 0.05 if you're going to call it significant. It's not like that. Okay, these are kind of like general guidelines. Okay, and they were proposed by Cohen, but he later opposed their use. Okay, so because people just really used them like they were cutoffs, but they're not. They're like sort of like a general kind of something to think about kind of a guideline. Okay. And the deal is that the what's small, medium, and large, it varies based on your field of study, the variables that you are working with. Okay. So you have to know see, I said I was going to say it again tonight. Here it is. You have to know the literature in your area if you're going to interpret effect size meaningfully. Okay. You have to know what for your variables in your field is small, what's medium, and what's large. Okay, so that being said, for the examples in class, like it's all make-believe stuff, right? Or it's stuff that like I just sort of like pulled out of a database and you don't know anything about it. So we'll probably use the 2, 5, and 8 thing. But for real research in the real world, you need the literature and you have to know it, and you have to know it well. Right? In fact, so like the recommendation I usually make to doctoral students is you should be reading 2 to 3 articles at least per week, so that by the time you're at your 3rd year and starting dissertation, you actually like know something about something, right? Okay. Okay. All right. So, quick side note: we talked earlier about causation, cause effect, and what it takes to establish that. Effect size is not related to the idea of cause effect. Okay. We're talking here about statistical effect, like how much influence or like how much can we explain, that kind of stuff. This like a large effect size doesn't mean that it is a cause-effect relationship. Like it's in no way implies that. Here's a statistical effect, not the idea of a practical cause-effect relationship. Okay. All right. So calculating D is so easy. All right. You're already halfway there. You already did half of it. I promise. It's the mean of the sample minus the mean of the population. You already did that. Okay. Over the standard deviation of the population. That's it. Okay. So easy. No square roots or dividing or nothing, right? So take, for example, the 2 that we did in the slides earlier, which would be this idea of value and their college GPA. So remember that value was statistically significant and college GPA was not. So when we look at value, we already did. Okay, when we look at value, we already calculated the mean difference to 1.24. The standard deviation was given at 1.23. Divide that as 1.01. D can be bigger than 1. Okay, most effect size statistics can't. D can. So don't freak out if it's bigger than 1. It happens, okay? The mean difference for college GPA was 0.05. Standard deviation was 0.63. So D is 0.08. If we use our sort of general guidelines, that would mean that for value, it's large, right? And for college GPA, it's not even small. Smaller than small. It's not surprising to be smaller than small because it is not significant. But I should say that that's not necessarily related, right? You could have a very small effect size but be significant. You could have a large effect size and not be significant, right? Because there's sort of this interplay about like, well, was it a very large sample? Well, then it's not significant. Could be a large effect. So you could have that sort of thing happen. Okay. If you have a negative value for the mean difference, which would mean that the population was greater than the sample, you'll have a negative D. So again, that's fine, it happens. But we usually report D just as the absolute value, so drop the sign. Because we don't care about the sign, right? We're just thinking about the magnitude, not the direction. Okay. Oh, that's not really okay. Okay, so what we'll do is for our same 2 examples, we'll take 20 seconds and calculate effect size, right? So D is equal to the mean difference. Okay, so what's the mean difference? It is -3, right? We already did it. And the standard deviation is 18, which is here, but it's also given here, right? So -3 over 18, it's technically negative 0.17, right? But we just use the absolute value at 0.17 for D. We don't care about the sign. So it's 0.17 or smaller than small, right? If we're using those general guidelines, which we will because we're not familiar with this literature. Okay. If we do it for the second one, we would have D equal to 32.6, again just taking it right from the numerator here, over 120, the standard deviation. Okay, well so that's 0.27, which would be a small effect.
So what if you got like 0.35?
For 32.6 over 120?
No. I mean like, just in another example, just
Oh.
say that your value was 0.35. Would you just say it's between the small and medium?
It'd be small. If you're using those guidelines, you probably call it small. Yeah.
Okay, you just kind of.
Yeah. Well, and again, unless you have, like, if you have evidence from the literature in your area that would lead you to believe it's medium, then you would say medium.
So we don't use a range like they're shown in the book. We want to just kind of round to either 0.2 or 0.5 or 0.8, I guess.
Yeah, that's the
Whatever's
recommendation from.
closest to.
Mm-hmm. Yeah, and so so just open back up the results, right? And so we now have an effect size. We could say the difference was small. D equals 0.27. Right? So we're reporting and interpreting the effect size as well. D is the simplest effect size because, as you see, all it is the difference over standard deviation.
You don't use the word effect size, you just say the difference.
You could. Like effect size if you wanted to. You could. Certainly could. So, so let's talk about writing this up. So, similar to before, we would want to start by saying what it is that we did and why. So, what did we do and why?
We're looking to see if the university engineering class is different from the university as a whole.
Uh-huh. And what did we do to do that?
Used a Z-test.
Okay, so like we used a series of two-tailed z-tests to determine if if A, I guess, senior level engineering class was significantly different from the university population.
Are you recording this?
Uh,
Okay.
on a number of key variables. Sure, they're key. These are key variables, absolutely. Okay. So then we would report what we found. And so the strategy that I would suggest, so we have a mixture here, right? Some were significant, some were not, right? And the strategy that I'm going to suggest is report your significant findings first and in more detail, and then your non-significant findings after that in less detail. And here's why, is that when someone is reading a manuscript, for example, or a dissertation, or whatever it is, they want to know about the stuff that was different, not the stuff that wasn't, right? People want to know about the interesting findings, and then it's okay that they're very happy for you to glaze over the stuff that sort of didn't matter, right? Unless that's the interesting part, you can just sort of, sneak it in there because you really ought to report it, but yeah. Okay, so like ACT, different, right? So we can start with saying like the engineering students were significantly different in terms of ACT scores. Z was 4.08 with P of less than 0.001. Reference was large in magnitude. D was, oops, I pressed something weird. Okay. Was 0.84. They were also significantly different in intrinsic value for, and let's just in self-reported for their coursework. Z is 4.96. P is less than 0.01. As well as self-reported utility value for their coursework. And I'm kind of like lumping those together because they're, they go together. That's why I'm putting those two together. And P for that is 0.022. The difference on intrinsic value was large in magnitude. D is 1.01, while the difference on utility value was medium. D for 7. Okay. There were no significant differences in terms of high school. Z equals 1.75, P equals O, and D equals 7. So why am I sneaking D right there? because it's not a significant difference, so why would I interpret the size of the difference, right? Doesn't make any sense to try to interpret the size of a non-significant difference, right? In terms of high school or college, C equals 0.38, P equals 0.702, D equals 0.08, grade point average. And we really should be putting means and standard deviations, right? But there's like so many of them. So what I'm going to do is say see table 1 for descriptive statistics. Okay, and we'll make that table, and that'll give us a great chance to talk about making tables, which is really exciting. I know. We've saved time just for tables. Isn't that great? Okay. Okay, so we need some sort of interpretive wrap-up statement, right? So looking at the results, what do you think? How are these students different from everybody else at the university?
Well, they put more, looking in the sense of, they put more value. Does it relate to that?
They tend to value their coursework more, looks like, yeah.
Yeah, they see more intrinsic utility value in their coursework.
Okay, and then that ACT score, what's it telling us?
Test well.
The test, or supposedly ACT is supposed to be a measure of preparedness, right? Whether you believe that or not is another issue. But so theoretically, right, it should be that based on these results, we'll start with these engineering students value seem to or higher value for their coursework and score higher on college placement tests than the university population. No, we don't see that in GPA, but we could probably explain that a number of ways if we wanted to in the discussion, right? Could be the nature of engineering coursework or something, whatever, right? So we need some sort of interpretive statement that's probably good enough without any literature. Okay, so so I know probably you all know how to use Word, but sometimes there's somebody who has never used Word before, so just in case that's the case. Yeah.
Question before we go on. I've seen in some instances, if there is no significance,
Mm-hmm.
say, don't even report the numbers. All you need to say is, there was no significance in these areas. Is there a school of thought on that?
I would always report, yeah.
Okay.
Mm-hmm. If you're going to talk about it, you need to report the
Well, say
statistic.
numbers for themselves.
Yeah. Uh-huh. Yeah, I don't want people to trust you, yeah. Because if I'm reviewing that, I don't trust you. Yeah. Okay, so yeah, don't hit enter like a bunch of times until you get to the next page. Okay. Instead, you insert, break, page break. So this is a Mac, so it looks different on PC. On PC, you have to like go to the Format tab and then go click the page break button, right? But it's the same basic concept. Don't hit enter a bunch of times. Instead, do insert, page break, which jumps to the next page. Okay. If you're doing tables, it's one table per page. Okay. Don't try to save space on that. One table per page. Now, if you're writing a dissertation, which I know several of you are in doctoral programs, if you're writing a dissertation, your dissertation advisor will tell you where to put tables in a dissertation because it's a little bit different than the manuscript layout. Okay. The formatting of the table is the same, but where it actually physically winds up in the manuscript is a little different and varies by advisor. So ask your advisor. right? Okay, so then we're going to say table 1, because it's the first one, right? Now, if I had a reference page, this needs to go after the reference page, right? So it goes references, tables, figures, appendices. Okay, that's the order, right? So, okay. Then if I'm going to have a table, I need to have a table caption, which in this case is, which is in italics, and in this case is descriptive statistics or key measures, which is probably about, should be as descriptive as possible. I just don't know how much better I can get in this case because I'm kind of trying to show a lot. Okay, so let me think about it. So I need like, what, like five columns, and I don't know, like a bunch of rows. I think 8. Okay. So maybe okay. And ideally, tables are double spaced. If taking a table out of double spaced will bring it from 2 pages to 1, it would be better to have a single spaced table than to have a table that's on 2 pages. Okay. But ideally, they're double spaced. Just like everything. Ideally, everything's double spaced. But sometimes you have to play with tables and stuff. Okay. So like this is going to be mean, and this will be standard deviation. This will be mean. This will be standard deviation. You know, ordinarily you can just abbreviate mean and standard deviation M and SD in italics. The reason I'm not doing that here is because, like, technically the abbreviation for a population mean is mu, and for population standard deviation is sigma, and so I'm just sort of like skirting that issue by using words. Okay. This is the only real time that comes up for us, but ordinarily we don't have population statistics to think about. But okay, then what I'm going to do is highlight these 2 cells and merge them, and so this will be for engineering students, and then this will be for university population. Okay, and then my rows are going to be ACT, high school GPA, college GPA, intrinsic value, utility value. Okay, and I want to put an extra row to delete it. Delete the entire row. Yes. Okay. And then this is bothering me, so I'm just going to fix it. Okay. So I'll enter the data. Make sure that, like in a table, for example, you would want to have the same number of decimal places on all of your, I mean, it's like throughout your paper, be consistent with decimals, but especially in a table, because otherwise it makes it look really, really messy, which is not good. You want clean tables. And so then this table gives somebody who, you know, maybe is interested to know the actual size of the difference instead of just the effect size. You know, like how many points are we talking about, for example, or to check the calculations or whatever it is that they're interested in doing. They can just go through and look at your actual statistics and do that. Which asking for descriptives is a really common revision that people request in research, as well as in dissertations, things like that. Oops, that's not right. Hold on. I got this one is wrong too. Okay. Okay, I think that's all right. If it's not, it's probably good enough. Okay. So then I'm just going to highlight all of these, and I'm going to left align them. The purpose of left aligning is now they're aligned by the decimal point, so the decimal point lines up for each column, which is visually appealing. Then what I'm going to do is I'm going to try to make the table kind of as small as possible. So I'm going to kind of pull the, I think that's going to be too close. Yep, that's too close. Kind of try to pull these lines over as much as I can. Oh, come on. There we go. See, now that sort of needs to be. Just try to make it like look kind of even, you know. And try to sort of even out those two. Maybe a little more. Maybe this a little more. Anyway, just try to make it sort of like roughly, you know, visually even. Okay, so it's still not APA style yet. You know, probably not shocking to you that APA style is pretty specific about what we want in tables. So I'm now highlighting the entire table. I'm going to go up here to this little like grid-looking button. Click the little arrow next to it. I'm going to remove all the borders from the entire table. So now it's just like totally blank of borders, no lines in the table. And I'm going to add to the top row a top and a bottom border. Because this particular table has sort of two headings, right? It has the heading that's like what group you're in as well as what the information is contained in each column. I'll add a bottom to this so that each of the heading rows gets like a top and a bottom line, and the very bottom row gets a bottom line. Okay, and so what that winds up then looking like is, let me make this a lot bigger. This is how it would actually print. And if you have questions about where to put, so horizontal lines are almost all you would usually see in an APA style table, except for there's some rare occasions where you get some vertical lines. But usually just horizontal lines. And if you have questions about where they go at a particular table that you're making, look at the table section of the APA manual. It has like a whole lot of examples, and you almost always can find an example that's pretty much the one that you're making right now. And just, oh, line goes here, goes there, goes there. Okay, I'm good, right? Yeah. And so this would be a really good example of when to use a table, because if I put all of these means and standard deviations up in the text, that's going to be really hard to read, right? But just saying, okay, they're there. You just have to go, you know, look at them for yourself when you want them. It's a lot easier. Okay. Easy enough. All right, and so for next week, we're going to be starting t-tests. The advice that I would have would be to make sure that you're very, very comfortable with the idea of hypothesis testing and what we're doing, okay? Because we're going to start learning a lot of different hypothesis tests. So it really helps if the idea of a hypothesis test is pretty comfortable, because, you know, then when you start like doing all sorts of different variations on that theme, if you get the general idea, that's really helpful. Yeah. Okay. So at this point,